All right, everyone, we're going to be talking about section 9.3, which is the normal distribution. This will be our very last section of our class, the last section that we have on chapter 9. So starting with just talking about the normal distribution, the times for 75 different transactions at a bank are recorded with results in the table below. The frequencies listed in the second column are divided by 75 to find the empirical probabilities. So normal distributions, these are going to be the tables that we often see accompanied with histograms and frequency polygons. So we see here we have this table, we have all of our different times, we have our frequencies, and then we have our probabilities, since we see that there is 75 transactions total. So we divide each one of these terms by 75 to get the probability. So then we can put them into a histogram with a frequency polynomial, like in figure 6 here. So we see our first image, we have our histogram with our values between 1 and 10, and then our probability here on the side, and then we use our frequency polygon, remember, to connect all of our midpoints of each one of the bars on our histogram. And this is kind of our first image here with figure 6a. So then we see that the times are estimated to the minute. But if we estimated to the second or even the millisecond, we would have a larger amount of smaller bars in our graph. So if we did milliseconds or even just seconds, we would see each one of these bars, if we were doing seconds, for example, each one of these bars would be split into 60 much thinner bars, and that they would also have different y values. So they would be much closer to this curve that we see here, our frequency polygon. And we would get a much more accurate representation if we broke it down by seconds instead of minutes. Then we see that this would cause a frequency polygon to look more and more like figure 6.b. So 6.b here is the same graph, it's just that now we have a frequency polygon that is much smoother, and then we just have the area underneath that is colored pink. So if we have smaller intervals on a wider period of time, we're going to get much more accurate representations, just like we have here in figure 6b. A distribution in which the outcomes can take any real number value within some interval is called a continuous distribution. So the graph of a continuous distribution is a curve. A continuous distribution just means that if we're looking at, for example, figure 7 here, that means that we have this curve, it doesn't stop, it doesn't shoot off somewhere towards infinity or negative infinity, and it doesn't have a break in it. It's just one continuous line, so we would call this a continuous distribution. So we see that figure 7 here is actually representing the continuous distribution of heights of college women. And we see that the most frequent heights occur near the center of the interval. And this is because we see here at the center, which is about 66, I believe this is in inches, we see that this is going to be the most frequent height. So our curve reaches its peak point at the most frequent interval we end up getting. So then another continuous curve, approximately the distribution of yearly incomes in the United States, is given in figure 8. So in figure 8 here. So we see between figure 7 and figure 8, we see that the peak is really much more towards the left side, or whatever value right around here would be. So we would see that this is going to be the most frequent area that we have. Instead of having it in the center, now it's definitely more towards the left. So we would say that this graph shows the most frequent incomes are grouped towards the left end of the interval, and we call this curve skewed since its frequent incomes are not centered. So if you ever see a normal distribution or a continuous distribution, and its peak value, it's not in the center, we call that skewed. And we can have skewed to the left or we can have skewed to the right. So in the case of figure 8 here, we see it is skewed to the left. And that's because we see that the most frequent income in the United States is definitely going to be more towards, or more, it's going to be closer to 0 than going to be closer to $200,000. So that's how we see it really skewed there to the left. Then we see that many natural and social phenomena produce continuous probability distributions whose graphs can be approximated very well by bell-shaped curves like in figure 9. So we're looking at figure 9 here. We see there are 3 different graphs, but they are all normal distributions. They all have their peak value there in the very center, even though that they have different shapes. So the very first graph that we see here in figure 9, this definitely has more of the shape of figure 7 that we looked at earlier, while the second figure is much taller and much thinner. And then we see our last part here, it's definitely much shorter and much wider. So even though they have different shapes, they all are recognized by having a bell-shaped curve. So these curves are example of normal curves which have normal distributions. So these are all normal curves, they all have normal distributions. And that just means that their most frequent entry is going to be in the center. We often use mu to denote the mean and sigma to denote the standard deviation of a normal distribution. And these things we went over in our last section as just some extra definitions. So we see mu, or the Greek letter mu, meaning our mean, is it going to be in the center. And then we would have our standard deviations on each side. So we usually see that our peak value is going to be at the mean for our normal distributions. So there are many different shapes of normal distributions, but they all have the following properties. Number 1 is that its peak occurs directly above the mean mu, just like each one of these in figure 9. The curve is symmetric about the vertical line through the mean. That is, if you fold the page along this line, the left half of the graph will fit exactly with the right half. That means that if we took, for example, in figure 9, our very first graph here, if we made a fold along the mean, if we folded it, it would look the same on both sides. Then for number 3, we have the curve never touches the x-axis. It extends indefinitely in both directions. So we see with each one of these, this one kind of looks like it does, but it does not technically. Your curve technically never touches the x-axis. The x-axis represents a horizontal asymptote. Then number 4, the area under the curve and above the horizontal axis is always 1. This agrees with the fact that the sum of the probabilities in any distribution is 1. So this means that if we took all of this area under our curve, it's going to equal 1, or 1 whole curve. All right, then we see a normal distribution is completely determined by the mean and the standard deviation, sigma. A small standard deviation leads to a tall, narrow curve, just like we see here in our second normal distribution of figure 9. So we know that a small standard deviation leads to a tall, narrow curve. So we can say, put a little star, we say this curve has a small, instead of writing out the words standard deviation, we're going to write sigma, because we know that that means standard deviation. Then we see that a large standard deviation leads to a flat wide curve, which is what our third curve looks like here in figure 9. So you can do the same thing. We say this curve has a large sigma. So we see these are the real differences between our two curves here, because they can have the exact same mean, but the only thing that changes it is our standard deviation. And we know that that just means the length away from the mean. All right, then we have our official definition from the book. We see normal probability. The area of the shaded region under a normal curve from A to B is the probability that an observed data value will be between A and B. So if we look at figure 10 here, we see we have a normal distribution, and then we have these little shaded regions. And in figure 10a here, this is just with real numbers, but in figure B, we have kind of these example numbers, so we would say between the values of A and B. So we would say that this shaded region is going to represent the probability that an observed data value is going to be between these two shaded regions. All right, so then to effectively use normal curves, we must be able to calculate the area under the curve. Luckily, the normal curve has been calculated with mean mu equals 0 and standard deviation sigma is equal to 1. So whenever we talk about normal curves, our mean is always going to be at 0 and our standard deviation is always going to be 1. This is called the standard normal curve. The key to finding the area under any normal curve is to express each number x on the horizontal axis in terms of standard deviation above or below the mean. So in this case, we would represent all of our values as our standard deviation, whether it's above or below the mean. So this means that it doesn't necessarily have to be a whole number. It doesn't have to be 1 or 2 or 3. It can be any number in between, and that way we can find our we can find the area under any normal curve using that value that we found. So now moving into the big part of this section is the z-score. So the z-score for x is the number of standard deviations that x lies away from the mean. So your z-score is always just going to be your number of standard deviations of whatever variable you have. We call this x, and how far away it is from the mean. So we see our z-score is going to be positive if x is above or to the right of the mean, and then it's going to be negative if x is below or to the left of the mean. So if we have a curve, we have another one right here. So if we look at this curve here, and our mean is going to be at 0, our z-score is going to be negative for anything less than 0, and then our z-score is going to be positive for anything greater than 0. So we can find the values of the z-score by using tables that list different values of z and the corresponding area under the normal curve. When we want to be solving for these z-scores and the area under the curve, we can solve for a z-score. We know how to do that. We did it in our, we will do it in this section. But what we really see here is that we want to find the corresponding value of the area under the curve. And the only way that we can do this is by using this table. Now, I took this table from a different website, but another table can also be found in your book. I'll also be posting this table that I found on the website if you would like to use it. So we see here that we're looking at negative z-scores. This first page is all just our negative z-scores. The lowest we can really go is negative 3.5. Really anything lower than negative 3.5, you're always going to end up with this 0.0001 value. And then we see that we increase until we get to our negative 0 point somethings. So these are always going to be the first few decimal places that we see. It's always going to be our first, it's going to be our whole number and our first decimal place. And then once you know these values, you go over here to find your next two decimal places, or your next decimal place technically, since your first decimal place is in the first column. It sounds a little bit confusing, but I promise as we go through, it will be a little bit more clear. Then we also see here, we have our positive z-scores. So we start at 0 and we go up to 3.5, and anything above 3.5 is going to be 0.9999. They also come with these really nice images. So with positive z-scores, we see our z above the mean. With negative z-scores, we see z is less than the mean. All right, so let's just start with example 1. We see example 1, we want to find the following area under the standard normal curve. And we want the area to the right of z is equal to negative 1.36. Well, if we look at our appendices here, or our list of values, each one of these are always from the left. It says it here, standard normal z distribution, cumulative area from the left. So it's always showing us this area from the left. Once again, from the left. It's not showing us the area to the right. So what we need to do in order to find the area to the right, so we can say, to find the area to the right, we take 1 and subtract our z-score. Since our z-score is taken from the left. And like we said in the very beginning, we know that the total area under our curve is always going to be 1. So if we find the area to the left of a z-score, if we take 1 minus that value, we're going to be left with all the rest of the area to the right. So we want the area to the right of the z-score. We see that z is equal to, we say z is equal to negative 1.36 is, and now we want to find the area under the curve. So let's go to our list. And we had negative 1.36. So looking at our list, the first thing we want to do, I'm going to track us, or I will track for us. So we have our value z, the negative 3.5. We see it's increasing. We want to go all the way down until we see negative 1.3. So we found negative 1.3. So let's highlight the row. All right, so this is our whole row of the values of negative 1.3. Now, remember our value was negative 1.36. So we need to get our second decimal point, our decimal place. So what we need to do is, if we're thinking of this is negative 1.3, this would be negative 1.30, negative 1.31, negative 1.32, negative 1.33, negative 1.34, negative 1.35, and negative 1.36. So now we want to highlight this column. You see negative 6, and we're going to color in this whole column. Now we covered in the whole column, and we're trying to find the area where they meet, or the spot in which they meet. And we see here that we're just, because we highlighted blue and yellow, the spot where they cross is going to be green. So we see here, we can zoom in. It's a tad bit blurry, but we see our answer is going to be 0.0869. So now we say z is equal to negative 1.36 is 0.0869 area under the curve. We're just going to have to scoot over our next problem. And remember, this value, this 0.0869, this is the area under the curve to the left. So to the left of this value, but we want it to the right. So remember, we take 1 minus 0.0869. And when we calculate this value, we're going to get 0.9131. And let's highlight this so we make it clear that this is our answer. And this would be area under the curve to the right. So that would be how we would find our area to the right of a curve instead of to the left of a curve. Now let's scoot over our next problem so we can have a little bit more room. So for part B, we want to find the value of z satisfying the following condition. 2.5% of the area is to the left of z. I believe there should have been a colon right there. So we want to find the z value. So now we have the area under the curve. We're finding the corresponding z value. So we see we're looking for 2.5% of the area is to the left of z. Well, first things first, let's put our percentage in terms of decimal points. Then we can use the table to find the corresponding z-score. All right, so we know that 2.5%, that's the same thing as saying 0.025. So we're looking for 0.025. So we can go up. It's a good idea to start on our first page here, which is our negative z-scores. We can also, if we observe this, we see that our lower values are going to be our negative z-scores, and our higher values are going to be our positive z-scores. So if we're looking for 0.025, we're really looking for a negative z-score because it's a pretty small number. So now we can use some different colors here. So let's do an orange, maybe a pink or something. So we pick orange first. Let's find 0.025. And this is going to take a little bit of searching. We're not going to find it absolutely immediately. We're just really looking for the place where we start seeing 0.02s or things along those lines. So we're kind of looking and, oh yeah, we found a 0.0025, but that would be 0.25%. We're looking for 2.5%. So we can kind of keep searching around. We keep looking. It looks like these are a lot of values that have 0.0. We're looking for 0.2. So we see here, we see some 0.1s, 0.1s. Okay, we're starting to get some 0.2s. 0.2, 0.2, we're searching. And we see here, we kind of realize that they're kind of jumbled. They're not always perfectly in order. They're kind of all over the place. So we're looking, And here we go. We see 0.0250. Coincidentally, this is in our same column as 0.06. So let's make a mark. Oh, that is not a pretty color. Let's pick a different one. Let's try out maybe pink instead. Ooh, that makes it pretty dark. These highlighting colors are a little finicky. All right, that's a little bit better. So we see our pink here. It's already in our column of 0.06. And now we can highlight our row. So our row in this case, we can fill in the rest of the row if we like, is negative 1.9. So this means that since it's in the column of 0.06 and the row of negative 1.9, it's going to be negative 1.96. So now we can fill in this value. Oh, let's circle this too so we know. And we can also just mark these so we can know which problems were which. So the yellow and the blue, that was going to be example 1A. Pink and blue was example 1B. All right, so now we come back down here. We found our value. We found 0.025, and we found the z-score that corresponds. So we can say the corresponding z-score is negative 1.96. All right, so when finding corresponding areas under the curves or corresponding z-scores, all you're really doing is being able to read the table and to find these values using your tables. All right, so now for example 2, and this is going to be your turn number 3 in your book. And we want to find the z-score for x equals 20 if a normal distribution has a mean of 35 and the standard deviation is 20. So we see, so we can say, we know the mean is 35 and the standard deviation is 20. And when we say the standard deviation is 20, this means that a z-score of 1, in this case, will be 20 plus 35. And a z-score of negative 1 is going to be 35 minus 20. So we say then z-score equal to negative 1 is 35 minus 20 is 15. So our z-score of negative 1 corresponds to the x value of 15. We'll say. And the z-score, which is equal to 1, is 35 plus 20, which is 55. So we see here the difference in our z-scores. If we're saying that x is equal to 20, then we need to find what value our z-score is going to correspond to x equals 20. We know that x equals 15 is going to be a z-score of negative 1. And let's make that a little bit clear here in our writing. So let's take the second part of this and move it down. So we can say that our z-score equal to -1. It's 35 minus 20 equals 15. So x equals 15 corresponds to z-score equals -1. Then we can say the same thing. So when we say then, and then we can move our second point that we had here. So then we say then our z-score, a positive one, is 35 plus 20 is equal to 55. So x equals to 55 corresponds to the z-score 1. And we're trying to find the z-score for x equals 20. So we want the z-score corresponding to x equals 20. So we see that our x value is 15 below the mean. And this is because we see that 35 minus 20 is going to be equal to 15. So we see that our x value of 20 is going to be 15 units below the mean. And we know that our standard deviation is within 20 units of 35. So we say then, and since our standard deviation is always the value of 20, it doesn't matter if it's 20 less or 20 more, standard deviation is always just 20. And we see that 15 is below the mean, or this value of 15, which we know corresponds to x equals 20. We say then -15 divided by 20 is equal to -3/4, or -0.75. This just means the z-score is -0.75. Now remember, when you calculate the z-score, you're always going to be dividing by your standard deviation, because you're only concerned with how far away your z-score is from the mean in terms of your standard deviation. So I know there was a lot of numbers that was thrown around, a lot of numbers that were very similar. But the main thing to understand is that if you had x equals 20, when your standard deviation cutoff would have been x equals 15, then you know that you need to take your values away, or the units away from the mean that the x value you're trying to find is, and you divide by your standard deviation. So what we found was that x equals 20, that was 15 less than the mean. Our standard deviation was 20, so we take -15 divided by 20. That's the main gist of our example 2 here. And what we can do from example 2 is that we can derive this general case for the z-score. So we say if a normal distribution has mean mu and standard deviation sigma, then the z-score for the number x is z is equal to x minus mu divided by sigma, which is just whatever x value you have minus the mean divided by standard deviation. Then we also have our definition of the area under a normal curve. In this case, we see the area under a normal curve between x equals a and x equals b is the same as the area under the standard normal curve between the z-score for a and the z-score for b. All right. Now on to example 3, which is also your turn number 4. This is going to be a word problem. So it's going to be a little bit different. What we see here, we have Dixie Office Supplies finds that its sales force derives an average of 1,200 miles per month per person with a standard deviation of 150 miles. Assume that the number of miles driven by a salesperson is closely approximated by a normal distribution. Find the probability that a salesperson drives between 1,275 and 1,425 miles per month. So, first thing that we really want to identify here is that you need to find the z-scores for both x, and we're going to label this x1, our first value here. x1 is going to be equal to 1,275, and then x2, our second value, is 1,425. So starting with x equals 1, so we can say x1 is equal to 1,275. And now we need to use this general case of the z-score here. We have z is equal to x minus mu divided by sigma. So we know x1 is 1,275. So then we're going to label this z1. This is our first z-score. And this is equal to x1, which was 1,275, minus the mean, which we know in our question was 1,200 miles. Remember, if we mention our average, that means our mean. So we have 1,275 minus 1,200 divided by our standard deviation, which was 150. So we take our z-score, z1, which is 1,275 minus 1,200 divided by 150. When we do this, we end up getting 75 divided by 150. This is just going to be equal to 0.5. So our z-score for x is equal to 1,275 is 0.5. Now we want to go on to our second x value, which is 1,425. Then we get z2, this is our second z-score now, is equal to 1,425 minus 1,200 divided by 150. Then we calculate this value, and we end up getting 225 divided by 150. Now we see here that this value is going to simplify to 3 divided by 2, or 1.5. So now that we've found our two z-scores, and we are definitely going to run out of room right now, so I'm going to kind of make these much closer together. Then we can scoop this up here. All right. So we have our corresponding z-scores to our x values, and now we really want to use the table to find the area under the normal curve. So you can say now you want to use the tables to find the area under the curve. And now if we're thinking about area under the curve, we're thinking about values between 0 and 1, so we can't have a negative value. So whichever z-score is going to be greater, that is what you're going to list first when finding the difference, because you can't have a negative area. So now we need to use the tables. So let's find first z1 is equal to 0.5 corresponds to and now we need to go to our table. So this is 0, that kind of looks like a 6, 0. So 0.5. So now we go to our table. We go to our positive z-scores. 0.5 is positive. And we want to find 0.5. No more decimal points after that, or technically 0. So we go to our table. We look for 0.5. If we start in our first column, we have z, which is 0.0, 0.1, 0.2, 0.3, 0.4, 0.5. So now we can highlight this row. And we want 0.50. So now we also have to think about the column of 0.00, because this would mean 0.50. So now we can use different color, and we're just going to go down to the value that we want, which is going to be 0.6915. Oh, that was wrong. Okay. So our z-score of 0.5 corresponds to 0.6915 area under the curve. So let's fill that in first. So we scroll down here, we say first z1 is equal to 0.5 corresponds to 0.6. I already lost it. 0.6915. And now we can do the same thing for z2 equal to 1.5. Where this is going to be our area under the curve. Then z2 is equal to 1.5. Corresponds to, and then we need to find this value as well. So we can use a different color here. So we go down, remember our very first column of positive z-scores, and we find 1.5. It's going to be this column here. And we also know that we want 1.50. So our second decimal point needs to be 0, which is also going to be the first column, just like in the first problem. We find this value, 0.9332. Let's do the same thing. Yeah. All right, so 0.9332. And this is area under the curve. Now, if we want to find the area in between which this is going to be the area in between. I just drew up an example of a normal distribution here. So if our mean here is 1200, our first value was 1275 and our second was 1425. If we have this shaded region, what we need to do is that 1275 represents any area to the left. Then 14.25 represents, again, all the area to the left. And what we need is what's in between, which we drew as these blue lines here. So we'll need to take our greater value, which is going to be 1425 in this case, and we're going to subtract 1275, and what we're going to be left with is the area in between. So this area here. So you can write that. So say if we want to find the area in between, we take our higher z-score and subtract the smaller. And when we say this, we're talking about the area under the curve. So we say we take a higher z-score. So let's rewrite this a little bit. So we say we take our higher, the corresponding area to our higher z-score. And subtract the area corresponding to our lower z-score. We do this because our question is asking us to find the probability that a salesperson would drive between these two values. So if we need to find the probability, this tells us that we need to find the area under the curve between these two values. So then we take Z2, which was 1.5, or corresponds to 0.9332. So we take 0.9332, which we say Z is equal to 1.5, this is Z2, minus 0.6915, and this is going to be Z1. Z1 is equal to 0.5. Now all we have to do is calculate this value. And when we do, we end up getting a value of 0.2417. We can say, or 24.17%. So now that we found this value, we say that 24.14% of drivers drive between 1,275 and 1,425 miles per month. We know that this also corresponds to 0.2417. And remember, when given questions like these, remember to think about whether you want to put it in percentage or decimal points, like if your question says round to 3 decimal points, or if it says put in percentage notation, then you know which one to write in. The values are equivalent. just know which one to use. All right, so moving on a little bit, we say, since z-scores are the number of standard deviations from the mean, so z1 corresponds to one standard deviation above the mean, then z-1 would be one standard deviation below the mean, and so on. If we look up z1 is equal to 1 and z2 there we go, is equal to -1 in the tables above, this shows us that 0.8413, which is z1, and 0.1587, which is z2, that is going to give us a value of 0.6826, or 68.3% of the area under the normal curve that lies within one standard deviation of the mean. This means that when we consider normal distributions, in general, 68.3% of the area under the normal curve lies within one standard deviation of the mean. Then we can extend this idea to two standard deviations. Then we see when z1 is equal to 2 and z2 is equal to -2, we get 0.9772, which was z1, and 0.0228, which was z2, is equal to 0.9544, or 95.4% of the area under the curve lies within two standard deviations of the mean. Then we see that these results are summarized in figure 21 and can be used to make a quick estimate of results when working with normal curves. We could also do this for three standard deviations. That would be z1 is equal to 3 and z2 is equal to -2. And we see that that gives us a value of 0.997, or 99.7%. So then we could say that 99.7% of the area under the curve lies within three standard deviations. So this is a general rule that we can come up with when we're working with our normal curves. All right, now on to example 4. Example 4 talks about annual bonuses. So salespeople of a large corporation received an annual bonus based upon their sales performance. The size of the bonuses was normally distributed with a mean of $12,000 and a standard deviation of $2,500. For part A, we want to find what percent of the salespeople received an annual bonus in excess of $10,000. Part B, we want to find what percent of the salespeople received an annual bonus between $10,000 and $15,000. Part C, we want to find what size bonus is exceeded by 75% of all other bonuses. And for part D, we're going to find the smallest and largest amounts for the middle 75% of the annual bonuses. So let's start with part A. I'm going to write part A on the side here. So we want what percent of the salespeople received an annual bonus in excess of $10,000. Well, if we're thinking about in excess of $10,000, we want more than $10,000. This means, so we can start writing this, we can say in excess of $10,000 means we want to find the area under the curve to the right of x equals 10,000. All right. So we need to find this value. So then first, we need to find the z-score for x. remember our z-score is going to be equal to x minus the mean divided by the standard deviation. So x we know is $10,000 minus the mean, which if we look at this, we say that the mean was 12,000 divided by, divided by our standard deviation, which we said was 2,500. Then we end up with the value of negative 2,000 divided by 2,500. This is the same thing as negative 4 divided by 5, or negative 0.80. Remember, because we want this in our table, so we need to have it in decimal point form. So we have a z-score of negative 1.80. Now remember, we're looking for the area under the curve that's to the right of 10,000. So we're going to find the area under the curve that corresponds to our z-score of negative 0.80. And then we're going to subtract that value from 1. So we say then the area under the curve that corresponds to z equal to negative 0.80 is, and now we're going to go back to our table and find our value. We see our value was negative 0.80. So we know it's going to be a negative z-score. Let's see, use purple color. And we see here we're going to go down to 0.08. So we have negative 0.8. We have a negative 0.8. We know this first column is 0, 0. So this value right here, 0.2119, that is going to correspond to the z-score of z is equal to negative 0.80. That's what it is. So we get our value of 0.2119. So scroll on back down to our problem. We see the area under the curve that corresponds to z equals negative 0.80 is 0.2119. Now, we want to find the area under the curve to the right of x equals 10,000. So remember, we take 1 minus the value under the curve, which was 0.2119, and we end up getting the value of 0.7881. All right, so we found this value. Then we can say, so 78.81% of salespeople received a bonus of more than $10,000. So that would be our value in this case. Now for part B. Now for part B, we want to find what percent of the salespeople received an annual bonus between $10,000 and $15,000. So remember, this is the same idea that we did for example 3. We want to find the area under the curve between two values. So we're going to let x sub 1 equal 10,000 and x sub 2 be 15,000. We already know the z-score. I'm just going to leave it there. We already know the z-score and area under the curve for x sub 1, which was z is equal to negative 0.80, and an area under the curve of 0.2119. So now we need to find these values for x sub 2. So remember, we want to find our z-score first. Let's find z-score first. And then we say that z2 is equal to our x value, which was 15,000, minus the mean, which was 12,000, divided by the standard deviation, which was 2,500. Now that we find this value, we're going to get 3,000 divided by 2,500, which is just the same as 6 divided by 5, or 1.2. Then z2 is equal to 1.2, corresponds to the area under the curve and now we need to use our tables once again to find the corresponding area under the curve to z equals 1.2. So now we're going to go to our positive z-scores. We have all of our values here. And we're going to go down to 1.2, and then we're going to find 0.0. So this corresponds to 1.20, this value right here, which is 0.8849. So we say here, area under the curve of 0.8849. So now that we've found these, now we can subtract the area under the curve corresponding to Z1 from the area under the curve corresponds, a lot of words, corresponding to Z2. This is going to give us a value of 0.8849 minus 0.2119, which is going to be equal to 0.673. Then we say 67.3% of salespeople receive a bonus between $10,000 and $15,000. All right, so now we can go on to part C. Part C wants to know what size bonus is exceeded by 75% of all other bonuses. So we're looking for the bonus that is essentially the marker for 25%. Because if we're looking for the bonus that is exceeded by 75% of all other bonuses, this means that all other bonuses are 75% above this value. And if we know that our whole curve represents 100%, then we're looking for the 20% mark, or 25% mark. So then for C, we say, since we want the value of X, or 75% of the area under the curve is greater then we are looking for the area under the curve left of 0.25 or 25. That 25% or 0.25. All right. So now we can say that we want to use our tables to find the area under the curve that represents the z-score corresponding to 0.25. Because we know our x value is going to be some value that's in the thousands, because we know that these are our x values. We're thinking about values like 10,000 and our mean is 12,000 and things like that. So we know our x value is going to be in the thousands. So if we're thinking about 75% or less of our area under our curve, that means we need to find the z-score that corresponds to 0.25. All right. So now we can go in and find the area under the curve corresponding to 0.25, or our z-score that's going to correspond to 25% of the area under our curve. We know that our lower values of the area under our curve are going to be in our negative z-score table. So we need to look in our negative z-scores. And remember, we're looking for 0.25. So we need to find the values of 0.2. So we see some values of 0.2 somewhere here along the bottom. So we can just start kind of tracking in order to find 0.25. We see here that we're looking, and we find this value, 0.2514. If we continue looking in our table, we see that we're not going to find a value of 0.25 exactly. So what we need to do instead is that pick a value that's the closest one. So we see here 0.2514, this is going to be the closest value we're going to get to 0.25. So we're going to take this value, and we're going to do the same things as we've been doing before. So we have 0.2514, that's going to correspond to the row of negative 0.6. And remember, we already know this value. We want to 0.2514. Now we can track our columns. We see that this is in the column of 0.07. We can color in our column here. So the area under the curve that corresponds to 0.2514 is going to be a z-score of negative 0.67. All right. So then we see, that 25% of the area under the curve corresponds to the z-score of negative 0.67. Now that we know our z-score, and remember the value that we want to find is x, we know the mean, we know the standard deviation, we can plug all of this into our equation for the z-score. So we can plug our information into the equation of the z-score to find our value of x. So we remember that z is equal to x minus mu divided by sigma. So we get negative 0.67 is equal to x, because we don't know it, minus 12,000 divided by 2,500. Now when we calculate this, we're going to get a negative 0.67 times 2,500 is equal to x minus 12,000. Then we can add 12,000 to each side, and what we end up getting is x is equal to negative 0.67 times 2,500, plus 12,000. Now we can calculate this value, and we're going to get negative 1,675 plus 12,000. And we're going to get x is equal to 10,325. In this case, it's dollars. So then for our final answer, we say, so the size of the bonus, oh my gosh, bonus exceeded by 75% of the other bonuses oh man, just woof, bonuses is x is equal to $10,325. And that's because since we knew that this value had to be exceeded by 75% of all other bonuses, then remember we take 100 minus 100% minus 75%, that gives us 25%. By finding that, by finding the z-score that corresponds to 25% of the area under the curve, or 0.25, then we were able to find our value of x using our z-score. Then lastly, we have part D, where we want to find the smallest and largest amounts for the middle 75% of the annual bonuses. So part D, we say that the lower z-value or z-score, which we're going to call z1, contains 12.5% of the area under the curve to the left, and the higher z-score, z2, contains 87.5% of the area under the curve also to the left. And this is because we're asking for the smallest and largest amounts for the middle 75% of the annual bonuses. And remember, if we're talking about the middle 75, when we draw out our normal distribution, we're going to get our curve here. We're going to say that's the mean. This is going to be our normal curve. And if we want the middle 75%, this means that we're going to take these values and we say that, I'm just gonna reset. We say that this is 12.5% and this is going to be 87.5%. We're finding the x values that correspond. So, since it was the middle 75%, that means that we have 25% left over, and if we know it's the middle, that means 12.5% on each side. All right, so then we can say, using the table, we can find the z-scores that correspond to 12.5% and 87.5% of the area under the curve. Then remember that 12.5%, that's like saying 0.125 corresponds to the z-score, or z1 equal to, and now we have to go to our table. So this is a lower value, 0.125. So we know that this is probably going to be a negative z-score. So once again, remember, we're just going to scan our values to try and find 0.125. Then we can do this, we can kind of scan our values, and remember, if we find a value that's very close to the value we're looking for, if we don't find it exactly, we can just pick that value. So we're looking, and we end up finding this value here. We have 1251. There is no value of 1250, so we're going to pick this value. Oh, it's really small, this value. Then we see, I'm really running out of colors here. We see that it is in the row of negative 1.1. I think I've used every color, I think. And the column of 0.05. Remember, we can color this in until we get to, and I kind of colored over it, but it is 0.1251. So we see that this corresponds to the value, or the z-score, of negative 1.15. Oh, I scrolled too fast. Okay. So we see 0.125 corresponds to z-score of negative 1.15. Then we're going to take the value of 0.875, and we're going to find that corresponding z-value. And we see z2. So 0.875, that's a pretty high area under the curve. So let's look in the positive z-scores. And now remember, we're looking for any value close to 0.875. So you can scan values here. We see this is 0.5, 0.6, 0.7, and we're trying to get around to our 0.8s. And we look, we get some 0.87s, and right about here, we have 0.8749. So we have 0.8749. This is in the column of 0.05. And also, I don't know how this is going to look. And I'm going to stop there because it's circled, and I'm pretty sure it would just make it so we can't see it. So we see here, this corresponds to the row of 1.1 and the column of 0.05. This means that it has a value of 1.15, which is 0.8749, which you know is really close to 0.875. So we see our new z-value of 1.15. Now we see here that our z-values are the same, except that z1 is negative and z2 is positive. But they're both 1.15, with z1 being negative 1.15 and z2 being positive 1.15. Now, then the shortest distance the shortest distance, 1.15 standard deviation from, below the mean. And remember, we're considering below the mean, so this is negative 1.15. Is, and we're going to say shortest, just going to write the word shortest, is equal to mu plus z times sigma. So we're going to take this value, and if we think about it, this is basically like saying x is equal to mu plus z times sigma, which is the same thing as when we just rewrote our problem. So we see that this is just x is equal to mu plus z times sigma. And we know our mean, we know our z-score, and we know our sigma value. So we can say that this is equal to 12,000 plus negative 1.15 times 2,500. And we see that our shortest distance, or in this case, the smallest amount, let's change this to smallest amount, not shortest, so smallest amount. This will be smallest instead. The same thing as saying x, let's call this x1 since this was z1. Then we see that x1 is equal to $9,125. Then the largest amount, 1.15 standard deviations above the mean, which we know is 1.15, is, how we say largest, is equal to mu plus z2 times sigma, or we know this is the same thing as saying x2 is equal to mu plus z2 times sigma. So we say x2 is equal to $12,000 plus 1.15 times 2,500. Now we can calculate this value, and we end up getting $14,875. This tells us the smallest amount, smallest and the largest amounts for the middle 75% of the annual bonuses are $9,125 and $14,875. All right, so that problem was very long. But we did see here that we really did work in a lot of these different ideas using our z-scores and our areas under the graphs, and then also finding our x coordinates that would correspond to these values. All right, so that was our very last section of our class. Stay tuned for the review, which is going to be tomorrow for your final. I will also be having extra office hours tomorrow as well, or on Wednesday the 12th. So you can feel free to pop into those. As always, if you have any questions or anything, feel free to email me. Pop into my office hours if you'd like, or submit an anonymous question to our online anonymous question form. All right, thank you all, and I will see you virtually later.